The universe is vast. We humans are curious, we want to explore. Now we have a new powerful eye. This eye is the James Webb Space Telescope, or JWST for short. Its mission is to look deep into the universe. It looks at distant stars and galaxies, and very excitingly, it looks at planets beyond our solar system. These are called exoplanets. JWST is helping us search for many things, including signs of water on these far-off worlds. What exactly are exoplanets? They are planets that orbit stars other than our sun. Thousands of exoplanets have been discovered. Our galaxy, the Milky Way, likely holds billions, perhaps even trillions of them. Some might be giant gas planets like Jupiter, others could be rocky, like Earth. JWST is designed to study some of these exoplanets in great detail. Why is finding water so important? Water is essential for life as we know it here on Earth. All living things on our planet depend on water. So, when we search for conditions that might support life elsewhere in the universe, water is a key ingredient we look for. Finding water on an exoplanet does not automatically mean we have found life. But it does mean that the planet might have the right conditions for life to potentially arise or exist. It is a very important first step in answering that age-old question: are we alone in the universe? We will explore how the magnificent JWST actually detects water on these distant exoplanets. It involves understanding light, incredible technology, and very clever scientists decoding messages from across the cosmos. So, let us begin this cosmic detective story. Light is amazing. It comes in many forms. The light our eyes can see is just a small part of it. This is called visible light. Think of a rainbow. It shows the different colors of visible light. But there are other kinds of light too. There is ultraviolet light, which can give us a sunburn. There are X-rays used in hospitals, and there is infrared light. Infrared light is basically heat radiation. You cannot see it with your naked eyes, but you can feel it as warmth from the sun or from a fire. JWST is specially designed to see this infrared light from the universe. Why is infrared light so important for JWST, especially for finding water? Many of the objects JWST wants to study are cool. Young stars forming planets are often shrouded in dust, and the planets themselves, especially those further from their stars, are not very hot. These cooler objects shine most brightly in infrared light. Infrared light can pass through cosmic dust clouds much more easily than visible light can. Water molecules, like all molecules, have a special relationship with infrared light. When infrared light of specific wavelengths passes through water vapor, the water molecules absorb some of that light. This absorption creates a unique pattern, a kind of signature. By looking at which infrared wavelengths are missing from starlight after it has passed through an exoplanet's atmosphere, scientists can tell if water is present. To detect these faint infrared signals from distant exoplanets, JWST needs to be incredibly sensitive. Its primary mirror is huge, over 6.5 meters wide. So, how does JWST actually get the chance to study an exoplanet's atmosphere? One common method is called the transit method. This happens when an exoplanet, from our point of view here in the solar system, passes directly in front of its host star. When the planet transits, it blocks a tiny fraction of the star's light. This causes a small, temporary dip in the star's brightness. Scientists can detect this dip with powerful telescopes like JWST. By observing these transits, we can learn the size of the exoplanet. We can also learn about its orbit. The real magic for atmospheric studies happens during this transit. As the exoplanet passes in front of its star, some of the starlight grazes the edge of the planet. This light passes through the exoplanet's atmosphere if it has one. The atmosphere acts like a filter. Different gases present in the atmosphere will interact with the starlight in specific ways. As the starlight streams through the exoplanet's atmosphere, molecules within that atmosphere absorb certain wavelengths or colors of light. Water vapor, as we discussed, absorbs specific wavelengths of infrared light. This altered light then continues its long journey through the vast emptiness of interstellar space, traveling for many light years. Section 4. JWST's amazing toolkit, the instruments that see the invisible. The James Webb Space Telescope is not just one single camera. It is a sophisticated observatory equipped with a suite of 4 powerful scientific instruments. Each instrument is designed to study the universe in different ways, capturing images and performing spectroscopy. For detecting water on exoplanets, the spectrographs are particularly important. The main instruments involved in this kind of work are NIRSpec, near-infrared spectrograph, NIRIS, near-infrared imager and slitless spectrograph, and MIRI, mid-infrared instrument. These tools work together, covering a wide range of infrared wavelengths, allowing scientists to get a comprehensive view of an exoplanet's atmosphere. Spectrographs are the real heroes when it comes to analyzing atmospheres. What they do is spread the incoming light out into its constituent wavelengths, much like a prism creates a rainbow from sunlight. This spread out light is called a spectrum. By examining this spectrum, scientists can see how much light is present at each specific wavelength. If a particular gas, like water vapor, is present in the exoplanet's atmosphere, it will have absorbed light at its characteristic wavelengths. Section 5. Decoding the rainbow, how scientists read atmospheric fingerprints. Once JWST's instruments have captured the light and spread it into a spectrum, the next step is for scientists to analyze this data. A spectrum is essentially a graph. It plots the brightness or intensity of light against its wavelength. Imagine a line graph where the horizontal axis shows the different wavelengths, or colors, of infrared light. The vertical axis shows how much of each wavelength was detected. If there were no atmosphere or an atmosphere with no absorbing gases, this graph might look relatively smooth. But the presence of an atmosphere changes this picture quite dramatically for specific wavelengths. Scientists carefully examine this spectrum, looking for telltale dips in the graph. These dips are called absorption lines or absorption features. They occur at the specific wavelengths where molecules in the exoplanet's atmosphere have absorbed the starlight. Each type of molecule, water, methane, carbon dioxide, and so on, has a unique pattern of absorption lines, like a unique barcode or fingerprint. So, if water vapor is present in the exoplanet's atmosphere, there will be characteristic dips in the spectrum at the known infrared wavelengths that water absorbs. Finding these specific dips is the key to detection. The process is like matching fingerprints at a crime scene. Scientists have laboratory data that shows the precise absorption patterns for many different molecules, including water. They compare the observed spectrum from the exoplanet with these known patterns. Section 6. Beyond the Horizon. Future quests of the Webb Telescope. The James Webb Space Telescope has already delivered some breathtaking results, but it is important to remember that its mission is just beginning. This magnificent observatory is designed to operate for many years, potentially a decade or even two. This means we can look forward to a continuous stream of new discoveries and deeper insights into the cosmos. The initial observations have proven its capabilities. Now scientists are eager to push those capabilities further, exploring a vast range of astronomical questions. One of the major ongoing quests for JWST will be to study a much wider variety of exoplanets. The first targets have often been hot, Jupiter-sized planets because their large atmospheres make them easier to study, but the ultimate goal is to characterize smaller rocky planets, perhaps even those orbiting within the habitable zones of their stars. These are the planets where conditions might be more favorable for liquid water on the surface. JWST will observe planets around different types of stars, including cooler, smaller M-dwarf stars, which are very common in our galaxy. Beyond just detecting water, JWST will be searching for a whole host of other molecules in exoplanet atmospheres. Scientists are particularly interested in finding biosignatures. These are gases that could indicate the presence of life. For example, on Earth, oxygen and methane in large quantities are produced by living organisms. Detecting such gases in an exoplanet's atmosphere, especially in combination, could be a very exciting hint, though not definitive proof, of biological activity. Section 7. Waterworlds and Cosmic Dreams. The bigger picture. Finding water on an exoplanet is a profoundly significant discovery. It is not just about ticking a box for a particular molecule. It is about understanding the conditions that exist on worlds beyond our own. Water is a crucial solvent for the chemistry of life as we understand it. Its presence in an atmosphere, or potentially as liquid on a surface, dramatically increases the chances that a planet could be habitable. When we talk about habitable zones around stars, we are talking about the regions where temperatures could allow liquid water to exist. JWST's findings help us pinpoint which planets in these zones actually possess this vital ingredient. These discoveries have deep implications for one of humanity's most fundamental questions. Are we alone in the universe? While finding water vapor in an atmosphere is a long way from finding alien life, it is an essential step in the right direction. It tells us that a key building block for life is present in other planetary systems. Each exoplanet found with water adds to the statistical likelihood that life might indeed be widespread. It fuels the hope that somewhere out there, among the billions of stars and planets, other living beings might be looking up at their own skies wondering, just as we do. The James Webb Space Telescope, with its incredible capabilities and the amazing discoveries it is making, does more than just provide scientific data. It inspires us all. It sparks curiosity in young minds, encouraging the next generation of scientists, engineers, and explorers. It shows what humanity can achieve when we work together on ambitious, peaceful goals. The images and spectra from JWST are not just for scientists, they are for everyone. They connect us to the cosmos. They remind us of the beauty and complexity of the universe and our small but significant place within it.